As we begin looking at binomial distributions, I want to begin by looking at an example to discuss where the formula comes from. A formula for a binomial distribution is n choose x, p to the x, q to the n minus x, where p is the probability of success, q is the probability of failure, P and Q are mutually exclusive. If you succeed, you don't fail, or if you fail, you don't succeed. So keep in mind that those are also the only two options. You either succeed or you don't. So when we add those together, those add up to 1. Or we could say that Q is the complement of P. Failure is the complement of success and vice versa. X is our random variable, whatever that may be. And it is just a count of successes. Now, we have to be careful with what we call success. In everyday events, success to us is something that is positive. It's a good thing. I'm successful if I make a good grade on my test. I'm successful if I get a job. I'm successful if something favorable happens. But in a binomial distribution, success just means that our random variable occurred. Whatever it is that I'm counting, then it's success if I find those. If I don't find the thing that I'm counting, then it's not success or it's failure. N is a number of trials. So recall that to be a binomial distribution, we have to have repeated trials, and those trials have to be identical. Or, in other words, the probability of success for each trial has to be the same. If my probability of success changes from one trial to the next, or if the look of my experiment changes from one trial to the next, then it's not binomial. But if my experiment is doing the same thing over and over and over, then those are repeated trials. So let's suppose that we have a multiple choice quiz and we have 4 questions and each one has A, B, or C. And this is a pop quiz and we don't have any idea what the material on the quiz is. So we are simply guessing each answer. So we want to find the probability of getting 4 correct. What is the probability of getting 4 correct? Notice we have 4 questions, so these are 4 trials. We're assuming that for each question there's 1 correct answer, so the probability of success for each question is 1 correct out of 3, so 1/3, which means the probability of failure is 2/3. Even though the questions are different, question 1 and question 2 are probably not going to be the same question, if we are simply guessing, that doesn't matter. We have a 1 in 3 chance of getting the first one right and a 1 in 3 chance of getting the second one right. So in sense of how likely is it that we get the question right, they are identical. So if we want to find the probability of getting 4 correct, that's the probability of getting the first one correct and the second one correct, and the third one correct, and the fourth one correct. These are independent. Another requirement for something to be binomial is that each trial has no effect on the others. So since these are independent, then our multiplication rule says that if we are looking for the probability of one thing and the next, we simply multiply those together. Now, if they were dependent, we would have some conditional probabilities, so forth. But since each event is independent, since getting the second one correct is not impacted by whether or not the first one is correct, they're independent, so we just multiply their probabilities together. So the likelihood of getting the first one correct times the likelihood of getting the second one correct times the third one times the fourth one. So the probability of getting all four correct, if I'm just guessing, is 1 out of 81. Or if we look at that as a decimal or a percent, that's 0.012, or about 1.2%. So, in other words, you need to study. Don't just go into quizzes and say, I'm just going to guess, I don't have a clue what's on there. It helps to know what you're talking about, because if you're just simply guessing, it's not very likely that you get them all right. Well, let's look at the case where someone says, I'm okay with not making 100. I want to know how likely is it that I get 3 correct. So if we want to get 3 correct, there's actually different ways to do that. We could either get the first one correct and the other one's wrong, or we could get the second one, sorry, I was getting 3 wrong. I could get the first 3 correct and the last one wrong, or I could get the third one wrong, or I could get the second one wrong, or I could get the first one wrong. All of those are ways of getting 3 correct answers. Well, the probability of that first thing happening is 1/3 times 1/3 times 1/3, but the probability of getting 1 wrong is 2/3. So that's 2 out of 81. Here, notice we have 3 successes. So we have 3 1/3 and 1 2/3. So the probability of that happening is 2 out of 81. Again, we have 3 successes, 1 failure. So that's 2 out of 81, and the last one is 2 out of 81. So the probability of getting 3 correct one way is 2 out of 81, but there are 4 different ways that we could get exactly 3 correct. So that probability is a good bit more. It's 8 out of 81 at least, which is about 10%, 0.099. So notice what we did. We found out what is the probability of getting 3 correct in one manner. This is one way of getting 3 correct. And then we saw that, well, there are actually 4 different ways of getting 3 correct. I could get 3 correct this way, or this way, or this way, or this way. So we take how many different ways there are of getting 3 correct times the probability of one of those, and that will give us that total probability of getting 3 correct. So that's what our formula does for a binomial distribution. P to the x, this is our probability of success, and this tells us how many successes are we dealing with. So in our last example, the probability of success was 1/3. We were looking at 3 successes. Q, that's the probability of failure. So for our example, that was 2/3. And its exponent is n minus x. It's basically how many remaining trials do we have. In our example, we had 4 trials. 3 of them were successful, but 1 of them was not successful. And then the piece that went out front is this n choose x. This is a combination. This is just counting how many different combinations are there of having x successes. So in our case, this would calculate how many ways are there of having 3 successes out of 4 trials. And we determine that by just listing our sample space for that. But as we have larger and larger experiments, then we have to do it by calculating a combination. So let's use our formula to find the probability of getting exactly 2 correct answers. Using our same example where the probability of success is 1/3, the probability of failure is 2/3. We're talking about guessing on our multiple choice quiz. So if we want to find out what is the probability of having exactly 2 right answers, so let's say that, exactly 2 correct. So our number of trials is 4. So we're looking out of 4, we're choosing 2. We have successes twice. And if we have 2 successes, that leaves us with 2 failures. Notice this is our x. This is our n minus x. 4 trials, 2 successes, so that leaves us with 2 failures. So number of successes, number of failures. If we have 2 correct, we have 2 successful questions, 2 failed questions. All right, well, let's do this calculation. So if we're calculating the number of combinations, it's our first number factorial over the second number factorial times their difference factorial. So let's calculate the combinations first. So 4 factorial divided by 2 factorial times 4 minus 2, so 2 factorial. So there's 6 different ways of getting two correct answers. If we do 1/3 squared, that's 1 squared over 3 squared. 2/3 squared, that's 2 squared over 3 squared. So if we multiply this together, 6 times 1 times 4 over 81. So that's the likelihood of getting exactly 2 correct, which 24 out of 81, 0.296. About 30% chance of getting exactly 2 correct. So this is what a binomial experiment is. Repeated trials that are identical. We have some successes. We're going to have some failures. We want to know how many different ways are there of having this number of successes, because this part only accounts for one of those, so we have to multiply that by how many different ways are there of having that number of successes when we have 4 trials. So let's do one or two more calculations here, actually, before we go on. Let's find the mean for this distribution. So we looked at earlier that the mean of a probability distribution comes from taking each value of our random variable times the corresponding probability and adding those up. But if our distribution is binomial, then we can get the mean by doing n times p, not times q, just n times p. So for our probability experiment, the mean is 4 times 1/3. So 4/3, or about 1.3 repeating. Remember what that means. This is the expected value. So if I take a quiz with 4 questions, each question has 3 choices, and I'm just guessing that on average, I'm only going to get 1.3 correct, which we can't get 1.3 correct. So I'm normally just going to get 1 right or occasionally 2. Now, yes, we could get 4 correct, we could get 3 correct, but just on average, we only get somewhere between 1 and 2 correct. So that wouldn't bode very well for our grade. Now let's find the variance. The variance is n times p times q. So for ours, 4 times 1/3 times 2/3. So 4 times 1 times 2 over 9. So that is our variance. And then our standard deviation is the square root of that, which as a decimal, that's 8 divided by 9, and the square root of that is about 0.943. So that just kind of gives us an idea of how spread our distribution is. All right, so might try a few more examples. All right, let's take a look at a couple problems. Before we do a calculation, let's look at 1 or 2 examples and determine whether or not they're binomial. Number 16 says you can draw 5 cards, one at a time from a standard deck. You do not replace a card once it is drawn. The random variable, so what we are counting, is the number of cards that are hearts. Now this is not a binomial distribution because the probability of success changes from each time we draw a card because we are not replacing a card. The first time we draw a card, we have 52 we're choosing from, but the second time we draw a card, we only have 51 we're choosing from. So regardless of what card we're drawing, the total number of cards is changing, so the probability of success is changing. So number 16 is not binomial. Now 18, a survey found that 42% of women ages 18 to 33 are mothers. 8 women ages 18 to 33 are randomly selected. The random variable represents the number of women 18 to 33 who are mothers. So we're looking at the population, we're choosing a woman, we're going to determine is she a mother or not. Then we choose a mother or a woman to see if she's a mother or not. So we're repeating, we're doing the same thing over and over and over. Since we're doing it out of the population, out of a large number, while we would not necessarily want to pick the same person more than once, we're not going to say, well, we're going to pull somebody and then we're not going to put them back in there, so our probability of success is changing, we're assuming a constant probability of success of 42% on each time. So in this case, we would consider this binomial because our probability of success is not changing from one trial to the next. So number 20 is similar to that. It's different, but it's similar. It says 36% of U.S. adults favor the use of unmanned drones by police agencies. We randomly select 9 U.S. adults, find the probability that the number of U.S. adults who favor the use of unmanned drones by police agencies is, and then they give us some choices. So X, our random variable, is going to stand for the number of people. What are we looking for? We're looking for U.S. adults who favor the use of unmanned drones. So we're counting the number of people in favor of drones. So X is just what we're counting. How many of the people that we have selected favor drones? We're randomly selecting 9 people, I believe it was. Yeah, selecting 9 people. Notice the first statement, 36% favor drones. So if we're counting people that favor, then we have a 36% chance of selecting someone who's in favor of it. So the probability of successfully picking one of those people is 36% or 0.36. So Q is the complement of that. So if there's a 36% chance on a single trial of selecting a person that is okay with drones, then there's a 64% chance of selecting someone who is not in favor of drones. Is what is the probability that exactly 4 people are in favor of drones? So that's the probability that X is exactly 4. So out of 9 people, we're choosing 4 to be in favor, or we're choosing 4 that are in favor. Our probability of success is 0.36. So remember, our exponent is the number of is how many successes we're going to have. The exponent for Q is how many failures are we going to have. So out of 9 trials, 4 were successful, so that leaves us the difference. So 5 failures. So if we need to calculate this combination, if we have 9 people and 4 are in favor, how many ways are there of selecting 4 in favor out of 9 people? So 9 factorial over 4 factorial times their difference, 9 minus 4 factorial, times the probability of success to the 4th power, the probability of failure to the 5th power, and now we just need to calculate that. So 9 factorial divided by the result of 4 factorial times 5 factorial. So there are 126 ways that we could select 4 people out of a group of 9. So we're doing that times 0.36 to the 4th times 0.64 to the 5th. So 126 times the result of 0.36 raised to the 4th times the result of 0.64 raised to the 5th. So 0.227. So about a 22 percent chance of getting exactly 4 people to be in favor of drones if we have 9 total. Now part B, slightly more complicated. What is the probability of having at least 2? Let's do this. Probability of having at least 2 in favor. At least 2 means greater than 2 or equal to 2, which that's the probability of having 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 successes. Now, these are mutually exclusive. If I have exactly 2 successes, then I did not have exactly 3, or I did not have exactly 5. So we have to calculate each of these probabilities, and OR means add. There are no overlaps to subtract because these events are mutually exclusive, but still, that will be a lot to calculate. If n equals 9, then our possible outcomes, we could have no successes, 1, 2, 3, all the way up to 9. So either no one is in favor of drones, 1, 2, all the way up to all 9 being in favor of drones. Notice this is asking for almost all of those. The only ones that it's not asking for is 0 and 1. So what we could actually do, remember, if we add all of those probabilities together, 0 all the way up to 9, those are the only choices. So if we sum all of the probabilities in our distribution, those total 1. If we know the probability of having no successes or 1 success, if we know this part of it, then the part we're looking for is just the complement. It's the rest of that. So, so the probability of having 2 or more successes, that's the complement of having 0 successes or 1 success. So what we'll do is, instead of taking the long route, we'll find the probability that x equals 0. We'll find the probability that x equals 1. We'll add those together. That will give us the probability that we don't need. Its complement will be the probability that we do. Just again, let's remember our probability function. We have 9 trials. The probability of success is 36%. Probability of failure is 64%. So if you tell me how many successes we're looking for, we put that in for x, and then we can calculate the probability of that number of successes. So let's find out. What's the probability that none of the 9 people are in favor of drones? So 9, choose 0, 0.36 to the 0, none in favor. And of course, if none are in favor, that means all 9 are against it. So 9 failures. So this is 9 factorial over 0 factorial times their difference, 9 minus 0 factorial, times 0.36 to the 0 times 0.64 to the 9. Well, when we do 9 factorial divided by 0 factorial times 9 factorial, that's just going to be 1. Anything to the 0 power is 1. So essentially our answer is going to be whatever we get with for 0.64 raised to the 9th power, 0.018. So that's the likelihood of getting no people in our group that are in favor of drones. Now let's find the likelihood of only one person in our group being in favor of drones. So this time, out of 9 people, 1 is in favor. So 0.36 one time, 0.64 8 times. Successfully finding someone, and then people that are not in favor. So 9 factorial over 1 factorial times their difference, factorial, times 0.36 to the first, times 0.64 to the 8. Why 8? Because that's n minus x. So 9 factorial divided by 1 factorial times 8 factorial. So that's 9 times 0.36 times 0.64 raised to the 8th power, 0.091. So we're probability of more than or at least 2. So what we found is a probability of none and the probability of 1. So those are the only ones not included in the probability that we want. So if we take those away from 1, that will leave us the probability of having 2 or more people in favor. So let's just put that in our calculator. 1 minus whatever we get when we do 0.018 plus 0.091. So 0.109 is what we get inside the bracket. That's what we're taking away. So 0.891. So almost an 89% chance that at least 2 people in our group are in favor of drones. Now let's look at a quicker way to do this. Our probability of success. Oops. Spoke too early. If our probability of success was a different number, there would be a faster way to do this. We actually did it the quickest way possible. But we have what is known as a binomial distribution table, but it only deals with certain values of p. If p is any of these values, then we can use this table to figure out those probabilities of success, those binomial probabilities. Notice on the left side we have 2 columns. We have a column for n. This is how many trials we have, and then we have a column for x's. So we don't have the p-value for our experiment in this table. But if we did, we would come down to where we see n equals 9. So we would use values in this region. This says n equals 9, and then this is the number of successes. So this is either no successes, 1 success, 2 success, 3 successes, and so forth. And then we would find the column that corresponded to our p-value. So for example, if our p-value was 0.55, we would be using this column. So let's just look at this specific number here, 0.213. That is the probability that when p is 0.55, n is 9, and x is 4. So if we're doing something where the probability of success is 55%, and we're doing 9 trials, and we wanted to know what is the probability of having 4 successes, that would be the value we would use. Again, that works really well if our p-value is something that's in the table, but if it's not, then we have to calculate these manually like we just got through doing. So let's do part C real quickly, or let's at least talk about it. We won't work all the way through it. Part C says, what's the probability that less than 7 are in favor of drones? I looked at the wrong one. Let's say less than 6. I'll get it right here in a second. So what is the probability that less than 6 people out of the 9 are in favor of drones? So that's the probability that none, or 1, or 2, or 3, or 4, or 5 are in favor. That only leaves out 6, 7, 8, or 9. So we could calculate these probabilities, and then what we're looking for is everything else. But notice we've calculated this one already, the probability of none of the people liking drones. We've done that one, the probability of 1 person being in favor of drones. We've also done that one. So we are only lacking those. So if once we find the probability of 2 people being in favor of drones and 3 people and 5 people, then we can add those together, and that will give us the probability that our number of people that like drones is less than 6.